Hello everyone and welcome back to my channel. Today we are going to look at the AWE64 memory interface. This is supposed to be a proprietary interface, but it is not really that complex. So today I want to try to explain what I've learned building these memory boards and how I ended up with my own PCB that is the MIDI Forge Rhapsody. And if you think that's brilliant, then you will enjoy today's video sponsor. More about brilliant later. So first let's have a look at the pinout of the pin headers that you can find on your AWE64 card. There are two pin headers. One is a 2x12 pin here in the top left corner, and then right next to it is a 2x13 pin connector. What is important to us right now are the SMA pins. They have these numbers in the parentheses, which we can ignore for now. And we have the SD pins. And as you can see, they're distributed among both connectors. So you have SMA on the 24 pin and SMA on the 26 pin header. And the same is true for the SD pins. You may already have guessed it, the MA is the memory address and the D is the data. We can ignore the S here. I believe this means sound card because this is coming from the sound card. Important for us is the MA and the D. So we have memory address lines and we have data lines. Now let's count the data lines first. We have 8 on this pin header and we also have 8 on the other pin header. So they're distributed equally among both pin headers. The memory address lines are also distributed and you will see 1, 2, 3, 4, 5, 6 and also 6 on the other pin header. So we have 16 data lines and 12 address lines. This is how the AWE64 interfaces with the memory chips. Yes, there are still other control lines, for instance the CUS and the RUS signal. How this exactly works, I don't want to get into it, but in short, to reduce the number of traces that we have to route to the memory chips, we can use the RUS and CUS signals to cut them in half. So if you want to know more about this, then maybe you should watch an older video where I'm explaining this in more detail. But for us, this is enough for today. And we also have a write signal. So this is used to either tell the memory chip you have to write the data into your memory arrays, or you have to retrieve data and send it back to the sound card. And now we have covered almost all signals except for the base M0 signal and the base M1. Of course, let's quickly have a look what these ones are about. So here is the memory upgrade module specification from Creative. You can find this online, but I'm looking for something very specific right now. And here are the two signals listed with different configurations. In essence, it means when both of the signals are high, I believe this is 5 volts, that means the sound card has 0 megabytes on board. If base M1 is high and the other one is low, we have 2 megabytes. Then we have this one, which is important because this is our configuration for the AWE64 Gold. And there's one more configuration when both of the signals are low. That means we have 8 megabytes on the sound card. I don't think there is any AWE64 that has 8 megabytes of memory on board, so I don't think this configuration is used. I know you can upgrade the value edition from 512 kilobytes to 2 megabytes by replacing the onboard memory chip, but I don't think that Creative sold sound cards with that configuration. So what is missing in this list is the standard 512 kilobytes that the AWE64 value was equipped with. And how I read that table is that you could technically use the onboard memory of your sound card in combination with a memory module. So you could use both the memory on the sound card plus the memory that is available on the memory expansion board. So the two signals that we have mentioned before determine the size of the downloadable RAM on the sound card. In other words, as it's written here, if both of the signals are found high, this was the configuration for 0 megabytes onboard memory on the sound card, the small DRAM on the sound card is ignored and address of the memory module starts from location 0. So basically, since you don't have any memory on board, you can only use the memory that is available on your memory expansion board. Whereas for the other three combinations, the size of the sound card DRAM is determined and the memory module offsets from the address accordingly. How I understand this is that the first part of the memory is always the onboard memory on the sound card, and then anything that comes after is the capacity on the memory module, up to 28 megabytes, because this is the limitation of the EMU8K chip that is on the sound card. And if I'm not mistaken, for the AWE64 value, both of these signals will be high, meaning there is 0 megabytes onboard memory available, and that is why on the AWE64 value, the onboard memory will be disabled when you add a memory board. I guess the 512 kilobytes don't make that much of a difference. I'm really curious what's going to happen when we don't populate the last two memory chips. This is U19 and U21. I would assume that on the gold version, you still get 28 megabytes, but on the value edition, you will only get 24 megabytes. So I had to quickly verify this. What I did is I popped out this last GAL chip from my memory module. You see this, the last GAL chip on the very right is out. So this is now a 24 megabyte module. But when I go to the diagnose application, you see that we still get the full 28 megabytes. So the offset is working properly. The MIDI-Forged Symphony behaves exactly like it is described in the specification. But now let's have a quick look at the memory chips I'm using. So here's the pin assignment of our memory chip, and you can see here these ones are all our data pins. These are 16, and this is also what we have on the AWE64 memory bus. We have 16 data pins. So this is straightforward, but then we have here the address pins, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we only have 10 address pins, but the AWE64 had 12. Remember, the memory address had 6 on each of the headers, so we have 2 extras. Now, unfortunately, the numbers here may be a little bit confusing, so let's ignore them. What we need to know is that 10 of these are connecting to the memory chip. So 10 of these memory address lines are connected to the memory chip. But what happens to the other 2? There are still 2 more memory address lines that are unused right now. And this has to do with how the memory chips are addressed. Now think about it. We have 16 data pins that come from the sound card, and we have 16 data pins on our memory chip. So that means one of these memory chips is saturating the entire data bus of the sound card. But we have up to 14 chips on the memory expansion board. They can't all be talking at the same time because the sound card wouldn't know which of the chips is reading or writing the data. And this is where all these GAL chips come in that are on the memory expansion board. The GAL chip is a generic logic array. You can program it and then it will execute the logic that you wrote. These chips are used to decode the memory addresses to know exactly which chip should be active at what time. And this is how 14 memory chips can interface with a Sound Blaster AWE64, even though it has only 16 data pins, exactly the same amount that we find on the memory chips. Now that we know how the AWE64 memory interface works, we should be able to build our own. And this is what the MIDI-Forged Rhapsody is. While I was puzzling through the AWE64's memory bus and coding those GAL equations, I realized how much fun it is to tackle complex problems like these. That is why I'm excited to talk about today's sponsor, Brilliant. It's like a playground for your brain, especially if you love coding and tech challenges like this. Brilliant helps you to get smarter every day with thousands of interactive lessons in math, science, programming, data analysis, and AI. Brilliant's lessons are hands-on, letting you dive into problems like debugging code or designing circuits, which is 6 times more effective than just watching tutorials. It's built by experts from MIT and Google, so you're learning the right way. Plus, their mobile app means you can sharpen your skills anywhere. If you're into coding, Brilliant's programming courses are a fantastic way to learn. Their Thinking in Code and Programming with Python courses teach you to break down problems, like designing a memory module, into manageable tasks. Ready to level up your coding and problem-solving skills? Visit brilliant.org/bits and bolts or scan the QR code on screen for a free 30-day trial and 20% off an annual premium subscription. Links to brilliant.org are also in the video description. Trust me, your brain will thank you. The first thing obviously that's very different are the memory chips. Instead of those larger 42-pin memory chips, we now have 26 or 24-pin SOJ chips. You can see these here. This is the pin assignment of these memory chips, and those are the ones that you can usually find on 32 megabyte SIM modules or 16 megabyte if they are single-sided. And what we can spot immediately is that these chips only have 4 data lines. 1, 2, 3, and 4. So instead of 16, we have only 4. That is already a big deviation of the previous design because we had one chip that could saturate the entire data bus. Now we have only 4 data pins. It would only cover 1/4 of the data lines. So in order to fix that, we would have to group 4 of those chips together, basically have the 16 data lines that are coming from the sound card distributed over 4 of those chips. So how can we get this to work then? The good news is This schematic looks a lot easier than the MIDI Forge Symphony. The Rhapsody is easier because the memory module doesn't have to decode so many memory addresses to address each chip individually. Now we have 16 memory chips on the board, but what we need to do is that we need to group 4 of them together that we can saturate the 16-bit data bus. So instead of switching between 14 different memory chips, we only have to switch between 4 different groups. And that makes it a lot easier to implement. As you can see here in the Rhapsody game, by the way, you can go to my website and play this yourself if you want to, we only have one GAL chip. We need to figure out a clever method how to access these 4 different groups. And this is literally my specification that I drew up in Paint how to design this board. This is how it started. Here in this picture, you will see different CAS and RAS signals. You see RAS 0, RAS 1, CAS 0, and CAS 2. This is something you will come across when you look at specifications of 72-pin SIM modules. This is, I guess, just convention. Our AWE64 memory interface only has one RAS signal and one CAS signal, but we have 2 of each in the documentation that I have here. So this one here requires 2 different RAS signals. Now the issue we are facing is that we need 2 of each signal. We need RAS 0, RAS 1, CAS 0, and CAS 2. And this is the responsibility of our single GAL chip on this board. Now I can also show you the equations, which are completely new. I know the SimCon uses equations, but as I understand, the SimCon has one version for the AWE64 value and one for the AWE64 Gold. And the equations cannot be used interchangeably. So you have a specific version for the Gold and a specific version for the value, unfortunately. These equations should work on any of the cards, and they should be compatible to the SimCon if you are using a 32 megabyte module. That's important. Only a 32 megabyte SIM module will work. And this makes the equations and the entire programming of the GAL chip a lot easier. And here are the equations. This is literally what is required. And you can ignore the lines from here. These are just comments. But yeah, these are the equations that are necessary to make the Rhapsody work on both the AWE64 value and the AWE64 Gold. But I'm almost certain that it will not take into consideration the 4 megabytes onboard memory on the AWE64 Gold. I just never tested this. By the way, these equations are not my brainchild. This was completely done with AI. 95% of this work is done by AI. I was only reporting back what works and what doesn't. And you know, it was kind of fun to have an AI buddy who tried its best to get this memory decoding done. One time I only got 8 megabytes displayed. One time I got 16 megabytes displayed. And then I used a thermal camera and noticed that only half of the chips are actually working. It was a really interesting experience to solve this problem. So here I'm sitting editing the video and I'm thinking about the 16 megabyte issue. Unfortunately, at that time, I didn't have this interactive Rhapsody board because it would have helped me to figure out which signal isn't working. Here is the thermal image of the Rhapsody that I took. And you can see here is supposed to be the A, then here is the W, and here is the E. And you can see that some of the chips are not visible. So we can see here 1, 2, 3, 4, 5, 6, 7, 8 chips that have a heat signature. The others are kind of dark. So let's make those, let's say blue. So this one is blue, this one is blue. Here is a chip, and here is a chip. Now this W is complete. Here is a chip, here is a chip, here and here. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 chips are not working. Now let's just try to remember a few of them because I have to switch back and forth between 2 windows. Let's just say this arch here, this is active. And this is actually why I started with this interactive board, because I wanted to know which chips are activated by the signals. So let's go for RAS 0 and CAS 0, and you see, okay, so we have these 4 chips that are active when these 2 signals go low, because they're active low. So RAS 0 and CAS 0. And these are 2 chips that were in our graphic here. So it was this chip and this chip. So that means RAS 0 and CAS 0 is working. Now let's move on to RAS 1. And we can see, okay, RAS1 and CAS0, these are chips that are inactive. So is the bar here in the A, then we have the W left and the two E's, top and bottom. So it was this A, the bar in the A, it was the left bottom of the W and the two bars on the E. So these ones are off. And all I did is I changed from RAS0 to RAS1. So maybe RAS1 is our issue. Let's go back to RAS0. So these ones we already checked. Let's move to CAS2 instead of CAS0. And you can see now we have this other chip here, and I think this one was active. Yes, so this is active, so I'm assuming we get all active chips. The chip in the A on the bottom right is active, yes. And then we have the W top and the E bottom. So it's the W top, this is the W, and the E bottom. So these are the chips that are active as well on our thermal image. So let's move to RAS1 and CAS2. We didn't have this one. And now we have top right A, middle W, and the E is the top left and the center. So let's check what we get on our thermal image. We have an inactive chip here. We have the middle of the W, which is inactive. And we had these two, this one and the middle one. So clearly our RAS1 signal wasn't triggered correctly. If I would have known this, maybe it would have been much easier to debug those equations that are used for the GAL chip. Now we also resolved another question. What about different capacities of this memory board? We just said I had 16 megabyte when the RAS signal was not working. So we had RAS0 and we can switch between CAS0 and CAS2. So these 8 chips, if you populate them, you should get 16 megabytes. Of course, if you only populate these 4, you have an 8 megabyte module, but this is a little bit low. But if you only have 8 chips, you can make a 16 megabyte Rhapsody board. So here we are. These are the 8 chips that need to be populated. And if you're questioning the layout, well, this has to do with the routing. This was just something that made it easier to route all these traces. I will not get into the details right now. But yeah, this interactive Rhapsody board would have helped me to figure out what was wrong with the GAL equations. Anyway, I thought this was interesting to share. Now let's go back to the rest of the video. By the way, the RAS and CAS highlights here have no effect on the game. You can just start over and you can rotate the chips with the letter R on your keyboard and they are going to snap into place. It does allow you to put chips in the wrong way. And if you check, well, then you will see what kinds of mistakes you made. So even if a chip is not properly aligned, even though it's there, but it's not correctly placed on top of the pads, you will not solve the puzzle. Yeah, so, and I think this is all I have for you in this video. I hope that this sheds a little bit of light into the AWE64 memory interface. Now, unfortunately, we will not see the Rhapsody edition today, unfortunately, because I need a little bit more time preparing the video. Nevertheless, I hope that you enjoyed today's content. So if you enjoyed it, please hit the thumbs up and subscribe to my channel if you haven't already done so. A big thanks to Brilliant for sponsoring this video. And finally, I also want to thank all my Patreons who are already supporting my work. And if you want to support my work, you can also head over to Patreon and pick one of the membership tiers. I also would like to get your opinion if you're going to my website and try to play this game. I want to know who can beat my score. Now here's the best score I got. Let me know if you can beat my record. Anyway, thank you so much for your time. Thanks for watching. And this is all for today. Take care and bye-bye.